Hello, I just spent way too long doing about half of the line integrals that are on the line integrals playlist recording them, before realizing that I did it all in portrait mode, and I wasn't happy with a lot of the commentary. So I'm trying spherical integration now. Let's see if we can get through all this in one take. It's kind of unlikely. So this is all the spherical integration problems from exam 2 and exam 1, exam 2 and the final, all smushed together from 2016, 17, 18, and what we have access to from 19. If only we had fall 2019, that would be pretty great. So let's take a look at this. We're converting a triple integral from rectangular coordinates to spherical coordinates. Okay, let's set up. Let's take a look at what our bounds are in here. So z is ranging from 0 to root x squared plus y squared, and we know that this is just going to be a cone aligned on the z-axis. So got our cone here, very crudely drawn cone, but it'll do. We also know that 0 is less than or equal to y, which is less than or equal to 4 minus x squared. Well, what's this thing? This thing is just going to be the upper semicircle on, well, it would help if I labeled these, on the xy axis with radius 2. So draw that in there. And it's undefined on z. So really this is coming up through our cone. And then finally, x is ranging from -2 to 2, which just confirms what we have drawn with our semicircle for y. Hemisphere, really. Nope, not a hemisphere. It's 2D. So we are looking at the intersection between these guys, and so our intersection area is really is going to be inside here, and so converting to spherical, we know that the angle formed between this cone, because it's just a normal, like, basic cone, is going to be, it's not drawn like it, but this is 45 degrees, and up here is 45 degrees between the cone and the z-axis, and the cone and the x or y axes. And so from this, we know that we want phi to range from pi over 4, which is going to be our 45 degree mark, all the way down to our xy plane, so pi over 2. Pi over 4 to pi over 2. And so one of our things that we're trying to solve for up here is this a value, which we just said has to be bounded on the bottom, or our phi has to be bounded on the bottom by pi over 4, because we want to skip everything from 0 to pi over 4. We don't want any of that, but we do want everything from pi over 4 to pi over 2. So automatically we have a 50-50 at getting the answer right. And the only other thing we're looking for is, it's very unclear here. If you just glance at it, we've got a B, D, P, it looks like a P, it's really a row, and then another D, which is, they could have chosen a different variable to make it a little more legible, but that's okay, because it's pretty easy for us to figure this out, because all we have to do is convert x into spherical coordinates and then tack on our sine phi rho squared. So we know that x in spherical coordinates is cosine of theta sine phi, and so adding that in with what we already have, which is sine phi rho squared. Oh, sorry, this is rho cosine. We find that we get rho sine squared phi rho cubed. Oh god, we get rho cubed sine squared phi cosine theta, and we see right here we have it. Okay, 12. I say 12, I have no idea what exam it's from, so that's useless. Let E be the region in the first octant that is inside the sphere of radius 1 and bounded by these planes, and we're computing this guy. And it's very common that they put z in the integrand for this, for spherical integration problems. Not exactly sure why. It does make you use a nifty little trig identity that otherwise they don't get to test, so maybe that's what they're looking for. But automatically, we're in the first octant, but if we graph this, it's looking like the constraints that they put on us is already putting us pretty much in the first octant with one little added constraint on top of there. So we're bounded, if we label our axes here, we're bounded by y is equal to 0, which is this whole plane here. We're bounded by z is equal to 0, and we're bounded by x is equal to y, which is just this plane that's running up out of the plane, up out of the page at us and back down to infinity. And so we see if we're bounded by all these three things, really it's this wedge in here that we're looking at. But also we have to consider that we're inside the unit sphere, so we can draw that on in here, which is just going to be this little volume in here, and we'll get rid of some of these lines to make things more legible. Oh, but not the, well, we just lost the whole axis, or whole y equals x. There we go. So here's our area that we are integrating under. We see that phi is running from 0 to pi over 2. We see that theta is running from 0 to pi over 4, because we could go through the whole conversion process, but the line y equals x, if we take a look at things on the xy axis, line y equals x, if we're bounded in between here, you can see pretty easily how that's a, that's a 45-degree angle, that's a 45-degree angle, so pi over 4 it is. And then finally, we know that rho runs between 0 and 1 because we're in the unit ball there. So setting up our integral and converting z into spherical coordinates, which is just going to be rho cosine of phi, then we tack on the rest, sine phi rho squared, so we can get rid of this guy and just cube our rho in here. From 0 to 1, d rho, from 0 to pi over 4, whoops, 0 to pi over 2, d phi, and from 0 to pi over 4, d theta. There's our whole integral, and now we just have to solve. So just doing the rho integral in our head, we're going to get p to the 4th over 4, evaluated on 0 to 1, which is just going to be 1/4 sine phi cosine phi d phi, that's a rho, d phi from 0 to pi over 2 as our next integral. And we know that 2 cosine phi sine phi is just equal to 2 sine phi, and that's a 5. It's not a 2. 2 sine phi. Nope, whoops, sorry. Cosine phi, sine phi is equal to 2 sine. Oh, God. I'm going to redo that whole identity. It was wrong another way. So 2 cosine of phi sine of phi is equal to sine of 2 phi. There we go. And so we can divide everything by 2 and substitute sine phi cosine phi for sine 2 phi, and our integrand becomes the integral from 0 to pi over 2 of 1/8 sine 2 phi d phi. That's a rho with a line through it, but okay. And then integrating negative 1/16 cosine 2 phi on 0 to pi over 2. Well, cosine of pi over 2 times 2 is just going to be negative 1, so this is 1/16, and this will this is negative 1/16, and so get rid of our graph for a second. Bringing everything else out over here, 1/16 minus negative 1/16 is going to be 1/8, and this multiplied by pi over 4 is our pi over 32. And there's our answer. Okay, question 15. We have another spherical integral for volume where they're using z and e, which is it's an interesting pattern that they keep up, except we're between the unit ball and the sphere of radius 2, but we're still in the first octant. So we can set this up with many fewer extra steps. There are no constraints on our first octant, phi or theta, so both of these are going to run from 0 to pi over 2. And we can see this as theta. If this is our x and y axis, we want positive x and positive y, and the only values for which x and y are both positive is from 0 degrees to 90 degrees, which is pi over 2. And then if we take a look at the, let's say, the zx axis, we know that phi is going to be coming down from this axis, and we want to remain within the first octant, so both z and x have to be positive, and so phi has to run from 0 degrees to 90 degrees to fill that whole first octant without going out. And then finally, our bounds on rho just run from 1 to 2, because remember, this is equivalent to saying rho squared equals 1 and rho squared equals 4. So 1 is less than or equal to rho, which is less than or equal to 2. And then we have a z in here, and just like we did up here, we're going to set up the exact same integrand, where z is rho cosine of phi. So rho cubed cosine of phi sine of phi, d rho, d phi, d theta. And we're actually not dependent on theta at all, so we can just multiply by pi over 2 and get rid of that to save some space. And we can pretty quickly do our rho integration here, where we're going to have p to the 4th over 4 evaluated on 1 to 2. This is going to be 16 over 4, and this is going to be 1 over 4. So overall, we're left with the integral from 0 to pi over 2 times pi over 2 of 15 over 4 cosine of phi sine of phi d phi. Now we can do that same substitution, double angle identity that we did earlier, and equate this to 15 over 8 sine of 2 phi d, not d rho, not again, d phi, integral from 0 to pi over 2 times pi over 2. Let's bring our 15 over 8 out for now. So we have 15 pi over 16, and do our antiderivative times the quantity negative cosine of 2 phi over 2 on 0 to pi over 2. And evaluating, this will be 1/2, this will be negative 1/2, so this everything in this quantity evaluates to 1, and we're multiplying by 15 pi over 16, and that is our answer. Compute the volume of the solid inside the sphere of radius 5, rho squared equals 5, and outside the cylinder of radius 4, aligned on the z-axis. So this problem, you certainly can go through all of the integration for it, but there's a very cool shortcut you can do. So this is actually, apparently there's a name for this. This is called the napkin ring problem. Well, this specific set of values is not the napkin ring problem, but we can solve it with a pretty interesting formula. So I'm just setting up, we have our cylinder running through. Oh no, there's a reason I'm doing engineering and not art, because this is bad. But if you can see, we have we have a cylinder running through a sphere, and if we take a cross section, let's say along the XZ axis, we will end up with this kind of ring looking, not ring, that doesn't look like a ring, but it forms a ring when we revolve it around, this kind of crescent moon shape. And as it turns out, there's a very nice formula for finding the volume of one of these napkin rings that just runs all the way around. And that is, let's see if I can remember it. Yeah, I can. Sweet. Is pi h cubed over 6. Yeah, pi h cubed over 6, where h is just the height of the napkin ring. So as it turns out, and I put a link to this on the spreadsheet, it does not matter the radius of the napkin ring. As you increase the radius of the napkin ring, and let's say if we increase it out to here, and with height constant, the width of the ring gets progressively smaller as you intersect a circle around it, but the volume of the entire ring actually remains the same. So it's only dependent on h. And in our case, what is h? Well, we have to figure that out. So we have, if we just look at a cross section, we have the circle of radius 5 and the cylinder of radius 4. So really, we can mark this as 4, and then a radius of 5 going out here. And since 3, 4, 5 is a Pythagorean triple, we know that this right here is 3. And you can do that yourself. Just root 25 minus 16 is 3. Okay, so we know that the height of our napkin ring is going to be 2 times 3, which is 6. And that will give us, if we plug 6 in here, we will get 36 pi. And we see, oh no, that's not one of our answer choices, but we forgot one of our constraints. Y has to be greater than or equal to 0. So this is going to give us exactly half of our napkin ring, kind of putting like a cutting plane in here. And we'll be left with our 18 pi. And one of these days, I'll get scared enough to actually go through the real integration for this one, because I know that on the exam they could easily throw us this, but with something in the integrand, which makes this whole method useless. But until then, I'm going to have fun with my napkin ring formula. Okay, yet another ZDV where E is bounded by a sphere. Oh, wow, okay. So this is, let's see, is this exactly the question that we had earlier? No, it is not, but we can go back up here and see that this is exactly the same question, except we are bounded by y equals x, which halved our volume. So we should end up with pi over 16, and if we don't, something is wrong with one of our questions, one of our answers. So this integral is pretty easy to set up. We've done it before. 0 to pi over 2, 0 to pi over 2, 0 to 1, rho cubed sine phi cosine of phi, d rho, d phi, d theta, and we're not dependent on theta in our integrand, so we can just change this to a pi over 2. My pi's get progressively worse. I had someone in public tell me, mention how I draw pi and how it's pretty weird, and I gotta agree. I'm sorry. I'm sorry I do this kind of stuff to you guys. But okay, so integrating, pretty simple. If we integrate rho, we're going to get rho to the 4th over 4 evaluated on 0, 1, which is just going to be 1/4 sine phi cosine phi integral from 0 to pi over 2 times pi over 2 d rho. And we know that we can do that substitution that we did earlier. I'm not going to show all of it, because hopefully you're watching this in one go. If you skipped, you might want to go back a little bit. And this will when we do the substitution, our integrand will become sine 2 phi over 8. And then taking our antiderivative, we get cosine 2 phi, negative cosine 2 phi over 16, evaluated on 0 to pi over 2. This is going to be 1/8. You can work that out for yourself if you want. We've essentially done the same question 3 times at this point, so I'm not feeling like going through everything. And then this guy multiplied by our pi over 2 is our pi over 16. And so either we've done something correct in both of these questions, or we've messed both of them up. So, but I'm pretty sure I remember the answers well enough to tell you that, you know, we got it here. Okay, convert the following integrals to spherical coordinates and compute it. So generally we're not given these, like, we're not asked to convert between, convert between coordinate systems on the final, but this is still good practice. So we can set up our coordinate axes to give this guy a graph. And we see that we're bounded on the bottom by y equals root, well, if we replace these guys with r, this is just going to be y equals r. Sorry, I don't mean y, I mean z equals r. And z equals r is just a cone, just our normal cone. And then we're bounded on top by the upper hemisphere of radius root 8. So let's see if I can, I've already set myself up for failure. Ugh, okay, that's not too bad. And since we know we're bounded on top, we want to have the area, the volume inside here. So really we're dealing with a snow cone shape where it's everything inside here. But let's see if we have any more more things to worry about here. We're bounded by, in terms of y, we're bounded by 0 to begin with. So that's going to be the xz plane, and we're bounded on top by the upper semicircle of radius 2. And so all this is going to be is this semicircle sitting here. And let's see, x is running from -2 to 2. So we know that it's going to be this entire semicircle. Okay, so now that we have our snow cone, and if I clean this up a little bit, really what we're dealing with is half of this snow cone, because we're bounded, because we're bounded on the bottom by y equals 0. I'm sorry, this picture is terrible, and I really apologize. But now that we know that we're dealing with this snow cone, we can set up our integral, and this is our integrand is just going to be 3 rho squared sine phi d rho. Rho is going to run from what to what? Well, we know that we're bounded up here by radius of root 8, so we need to run from 0 to root 8, and then we're bounded we're bounded on phi by, let's see, well, we want all of this volume between 0 and 45 degrees, so 0 to pi over 4, and then as far as theta goes, we know that we're running this entire semicircle, so pi. Okay, so now evaluating, if we take our integral with respect to rho, we're going to get rho cubed on 0 to root 8, which is going to be 8 root 8 sine of phi, adding the rest of our integrand back in, from 0 to pi over 4 d phi. Integrating, we're going to get 8 root 8 times the quantity negative cosine of phi on 0 to pi over 4. Well, cosine of phi on 0 is going to be, negative cosine of phi on 0 is going to be -1, whereas this is going to be negative root 2 over 2. Okay, doing this problem for the 3rd time because I messed up 2 minor things twice and then had little, meltdowns over it. We are going to try this integral again and hopefully not have to do it for a third time. Sorry, fourth time. This is time number 3. Oh my god. So we're dealing with a region above a cone and below a sphere. We can rewrite this cone as root 3z equals r, which we can think of as for every unit z that we move up, we move over root 3 units. So our our cone is going to have an angle like this, which when you work through it ends up being, if our z-axis is here and our x-axis is here, this in here is an angle of pi over 3, which is important for our phi bounds in a bit. And then we're bounded on top by the sphere of radius 10, radius root 10, and if we draw this out, this is going to, this entire shape is going to look something like, nope, no, it really won't look like that. But that's a good artist's rendering. So we have our angle of pi over 3 for phi and our radius of root 10, and we have enough to set this integral up. Well, we're not dependent on theta at all, and we know that because our integrand, all we're adding is a rho, because the square root of rho squared is just rho. So we can add a 2 pi out there instead of integrating from 0 to 2 pi on theta. Then for phi, we know that we're running between 0 and pi over 3, and for rho, we're running between 0 and root 10. And then our integrand is rho to the third, sine phi d rho d phi. So integrating rho to the 4th over 4 on 0 to root 10, this is just going to be 25, which will go stick out with our 2 pi to get 50 pi times the integral from 0 to pi over 3 of sine of phi d phi, and integrating all this in here is just the quantity negative cosine of phi on 0 to pi over 3, which will be negative 1/2 and negative 1, which evaluates to 1/2. And 1/2 times 50 pi is our 25 pi answer. Thank God I get away from this question now. Okay, find the volume of the part of the unit ball, radius 1, centered at the origin, that lies between the cones phi equals pi over 6 and phi equals pi over 3. So this will be pretty easy to set up. We're not dependent on theta at all, so we can put a 2 pi outside of everything. As far as phi, we're running between, they just give it to us, pi over 6 and pi over 3. And for rho, we're running between 0 and 1. And then since we have nothing in our integrand except for rho squared sine phi, like always, d rho d phi, we can solve. Rho cubed over 3 evaluated on 0 and 1 is just going to be 1/3. 1/3 sine phi integral from 0 to pi over 3 d phi. 2 pi is what we're left with. And if I can get the eraser out, integrating, we get 2 pi times the quantity 1/3, negative 1/3 cosine of phi on 0 to pi over 3. Well, pi over 3, sorry, how did I lose my pi over 6? This is pi over 6, by the way. And same over there. So pi over 3, cosine of pi over 3 is going to be 1/2, so this will be negative 1/6. And cosine of pi over 6 is root 3 over 2, so this will be negative root 3 over 6. So putting everything together, we have 2 pi times root 3 over 6 minus 1 over 6, which is the same as pi over 3 root 3 minus 1. Okay, this is why you got to be careful, because I just did this whole integral once and forgot that there was a z in the integrand even after mentioning it. allowed. So I got to do this whole thing over again. And that's a very easy thing to just to screw up in an exam. And I would have just done it right there. So, you know. Okay, so the next integral that we're dealing with is, let's see, we're inside the sphere of radius 2 and above the cone phi equals pi over 3. So we're dealing with this spherical cap with an angle of pi over 3 off the z-axis, and it will look like a our snow cone shape that we know and love. So rho is going to run between 0 and 2. Phi is going to run between 0 and pi over 3. And since we're not dependent on theta, let's go set up our integrand, not forgetting that z like I did last time. We're going to get rho cubed sine phi cosine phi d rho d phi, and then we're not dependent on theta at all, so we can put a 2 pi out here. Okay, evaluating. Rho to the 4th over 4 on 0 to 2. This is just going to be 4. This is going to be 0. 4 sine phi cosine of phi is our new integrand, but we can take that and do a nice little substitution to change that into 2 sine 2 phi, integral from 0 to pi over 3 d phi. And integrating, we will get negative cosine 2 phi on 0 to pi over 3. And let's see, the cosine of 2 pi over 3 is going to be negative 1/2, and we have another negative out there, so this will cancel out, and we'll get 1/2, and this will be negative 1. So overall, this whole guy evaluates to 3/2, and then we got to go remember what we had sitting out here, which was our 2 pi. 2 pi times 3/2 is 3 pi. Okay, we're almost done, I think. We're computing this integral where E is the region bounded by the sphere of radius root 2, because rho squared equals root 2, rho squared equals 2, rho equals root 2. So setting this integral up, it's going to be the integral 6e to the rho squared to the 3/2, which is going to simplify down to rho cubed. And then we need to add in what we always have for these spherical integrals, which is rho squared sine phi d rho d phi, and we're not dependent on theta, so 2 pi on the outside. Okay, and let's set up our bounds. We know that rho is bounded by 0 and root 2, like we established up here, and phi is not bounded by anything, actually, so 0 to pi. And we are ready to integrate. So we can do a nice u substitution where u is rho cubed and du is 3 rho squared. We can divide out a 3 rho squared d rho. Don't want to forget that. So we can let's move this sign out one step and just deal with the integral from 0 to root 2 of 6 rho squared e to the rho cubed d rho. And so we can divide out a d rho 3 rho squared, and we're going to get 2 e to the u du, and our new bounds of integration are 0 and 4. So integrating, we will get 2 e to the u on, yes, yeah, that, nope, no, okay. See, I thought there was something wrong. Let's rewrite this. Our upper bound will not be 4, our upper bound will be 2 root 2. So this will actually be 0 to root 2 root 2 e 2e to the u du. So the integral of 2e to the u is just some more 2e to the u. So we can evaluate, and we will get 2e to the 2 root 2 minus, well, e to the 0 is 1, so minus 2. And then all of this is now multiplied by our integral from 0 to pi of sine of phi, and also our 2 pi. So we'll put our 2 pi out there, and I'm running out of, nope, don't want to delete the integral itself. We're running out of space over here, so we'll get rid of some of this, and all we're left with is this guy multiplied by sine of phi d phi from 0 to pi. And this is negative cosine of phi on 0 to pi, which is 2. And so putting everything together, we get 8 pi e to the 2 root 2 minus 1, which is, thank God, the correct option. Okay, the equation of the surface rho equals pi over 4 converted to cylindrical coordinates becomes, okay, let's take a look at this. If we draw, say, this is the x-axis and this is the z-axis, we know that phi making an angle of pi over 4 means an angle of pi over 4 coming down from the z-axis. So this is 45 degrees. And we know that we're not bounded on theta at all, so this guy will actually be revolving all the way around. And we want to convert this into cylindrical coordinates. This is looking very much like a normal cone. And so, in fact, if we set up our cone, z equals root x squared plus y squared, we know that this thing also makes an angle of 45 with the z-axis, and we can replace our x squared with plus y squared with r squared and find that z equals r. Okay, we're evaluating this integral. Oh, thank God, I only have 2 left. Okay, we're evaluating this integral where it uses a region in the first octant bounded by the sphere. I'm not going to do this one, only because we have done exactly this question before, and it's right here. So I don't know. Skip back to that part. That's it's kind of funny. I've never found a question that was legitimately identical to one that they've asked in a different exam, but here's one, and I'm not doing it. So scroll back if you want to see that again. I don't know why you would. Okay, now we're evaluating the triple integral, where E is a solid region in the first octant outside of that sphere and inside of this sphere. So first off, we got to figure out what's going on in our integrand because we're not used to having x's and y's in here. So x in spherical coordinates is cosine, my thetas keep looking like phis, cosine theta sine phi, and y is equal to sine theta sine phi. So we can plug everything in here, and we'll see that x squared is cosine squared theta sine squared phi, and y squared is sine squared theta sine squared phi. Sorry for the noise. And so we can factor out sine squared phi from everything, and we're left with cosine squared plus sine squared. And so all of this simplifies down to sine squared phi. And so we know that also in our integrand, we're going to have our basic building blocks that we always have. So this is going to be rho squared. Oh, sorry. This is supposed to be, rho cosine and rho sine in there. So in fact, this is going to simplify to rho squared sine squared. So really this is rho to the 4th, sine to the 3rd, phi, d rho, d phi. And let's take a look at our bounds. So we're outside of the sphere of radius 1 and inside of the sphere of radius 2. And we're in the first octant, so we know that both phi and theta have to be from 0 to pi over 2. And so we can evaluate. It's a little scary that we have a sine cubed, but I think think it'll be okay in the end. So rho to the 5th over 5 on 1 to 2 is going to be 32 over 5 and 1 over 5. So 31 over 5. These are some pretty yucky numbers, but it'll be okay. 31 over 5, and we'll set up our integral again over here from 0 to pi over 2 sine cubed phi d phi, which we can evaluate using some u substitution and a little bit of trickery, because this is equivalent to 31 over 5 sine of phi sine squared of phi, which we can then mess with some more. I don't know why I said 5 and I wrote 3, but that's supposed to be a 5. And so we can mess with that some more and get 31 over 5 sine of phi 1 minus cosine squared of phi. And this is still an integral from 0 to pi over 2 d phi. And we can do some u sub. So we'll set u equal to cosine phi and du to negative sine phi d phi. And so rearranging everything, we're going to get the integral from 1 to 0 of negative 31 over 5. We're dividing out that sine phi, and then 1 minus u squared du. So we can reverse the bounds of integration and cancel that out with the negative over here to change this to an integral from 0 to 1. And we can take this constant 31 over 5 and move it out. So all we're left with is, oh no, we lost our 1. Let's see if we can get it back. Whoop. I guess that's okay. And so all we have to do is evaluate this, which is going to be u minus u cubed over 3 evaluated on 0, 1, which is just going to be 2/3. And 2/3 times 31 over 5 times the pi over 2 that I left a long, long time ago is going to be 31 over 5 times pi over 2 times 2 over 3. These 2's will cancel. This is 15. This is 31 pi. And there we go. Yeah, that took a while, but I hope that was helpful. Please let me know if there are any issues with these. I'll go and edit up a corrected explanation. Thanks for watching, I guess.